By the way, I had actually forgotten to mention something in the previous video, which is that we were actually just doing a special case. When we were doing that direction of the theorem, we were doing a special case of this exercise. There's this general fact that if A is a subset of B, then the identity function on A can be used as an injection from A to B. So there exists an injection from A to B. From the standpoint of thinking about cardinality and the sizes of sets, this should make sense, right? We think of the existence of an injection from A to B as indicating that A has no more elements than B has. And if A is literally a subset of B, if the elements of A are all just elements of B, then that should be the case, right? That A can have no more elements than B has. Maybe I'll give a small warning here that that kind of reasoning that, oh, this makes sense that this be true, thinking about numbers of elements, can quickly mislead. So it's true that if A is a subset of B, then there exists an injection from A to B. But it's possible to have the following situation, and it's quite common. You can have A be a subset of B. You can have it actually be a proper subset of B, which means a subset but not equal. So you can have A sort of contained inside B and not equal to B. So it's strictly sort of a smaller set, but they can still have the same cardinality. So even though B has some things that A doesn't have, even though it looks like B has more elements than A, in the sense of cardinality, you could still have them have the same cardinality, meaning there could still exist a bijection between two sets, even when one set fully contains another and contains more things than that. We are not actually running into this because this you need to start looking at infinite sets to start running into this, and it will not happen with finite sets. But it is definitely a common situation and throws people off when they first run into it in their study of cardinality. So just because a set like B has more elements, just because a set has elements that another set, that one of its subsets doesn't contain, that doesn't mean it has more elements in the sense of cardinality, in the sense of whether or not there exists a bijection. So if you're curious about that later on, and you want to see an example, I recommend looking over at Theorem 135, Hilbert's Hotel. Let me pull up the notes version. So the theorem says that next of the natural numbers is in bijection, or there exists a bijection between next of the natural numbers and the natural numbers. Now, the set of natural numbers we haven't proven, but you will find is an infinite set. When you apply next to it, which is something we've actually not done before, what you get is the set of natural numbers, but with one more element thrown in. So this is an infinite set with an additional element thrown in. If you try to think about like how many elements does this have, you might think infinity plus 1, because it's starting out as an infinite set and then you're adding one additional element. Now this is a situation where this is a proper subset of this, right? The set of all natural numbers is a subset of the set of all natural numbers plus one additional element. And this one contains something that this one doesn't. So you might think, oh, this has more elements. But cardinality doesn't notice that. There still exists a bijection between these two. And here's kind of a picture of the bijection. So if you imagine, so I'm going to set up the bijection so that it goes from here to here. So this will be the domain. So this will be the set of natural numbers plus an additional element, which is actually the set of natural numbers. And the codomain will be here. So these guys you see at the top, these are all the residents of next n. So these all, 0, 1, 2, 3, etc. These are all natural numbers, these guys. And This guy, the set of natural numbers, is a new additional resident that we're introducing who lives in this set, right? Next of a set is the set with the original set thrown in as an element. So next n consists of all the elements of n. Sorry, the highlighting is weird. Consists of all these elements of n plus n itself thrown in as an additional element. So these are all the elements of next n. Then how do we map them into n? So let's say these are the doors of our hotel labeled by natural numbers. How can we map them bijectively? And then here's the idea. Send Mr. 0 to door number 1, send Mr. 1 to door number 2, and so on. If you do this, then you have, at least here, ignoring this portion of the picture, at least here, you have a bijection. And you've now created a space, the 0 door, for our additional new guest. So when people talk about Hilbert's hotel, they're referring to an infinite hotel where there's a door for every natural number. And the idea is that in Hilbert's hotel, even if it's full, you can accommodate a new guest by just shifting everyone one door over and then bringing the new guest into the empty space. So yeah, you can totally start out with a set like A and then enlarge it into another set B and then not actually increase the number of elements in the sense of cardinality. And this will often happen to you when you're working with infinite sets.